Hello and welcome to Kognito Key. Ever wonder about the invisible forces that make our world tick? Today, we're pulling back the curtain on a secret that's hiding inside all sorts of things, from the transformers on our streets to the wireless chargers on our desks. It's a really cool piece of electrical science, so let's jump right in.
So, you've seen these, right? These gray boxes on power poles, or maybe the little power brick for your laptop. They're called transformers, and their whole job is to change electricity, to step the voltage up or down. But here's the wild part. The two main circuits inside aren't even touching. There's a physical gap between them. So how on earth does the electricity get from one side to the other? It almost seems like magic, but I promise you, it's pure science. And the answer to that puzzle is this amazing thing called mutual inductance. At its heart, it's all about influence. It's the ability of one coil of wire to have an effect on another coil that's just sitting nearby. Think of it like an invisible handshake, a way for two totally separate circuits to communicate without ever making physical contact. But how does this invisible conversation actually work? Well, it's all built on one of the most important rules in all of physics, Faraday's law of electromagnetic induction. Now, what this fancy phrase really means is actually pretty simple. If you have a changing magnetic field near a wire, it will create a voltage in that wire. And the key word there is changing. A steady, boring magnetic field does nothing. It's the change that creates the magic. Okay, so let's walk through it. Imagine we have two coils, right? Let's call them coil A and coil B. First, we send a changing electric current through coil A. Step 2, that current creates a changing magnetic field around it. You might hear this called magnetic flux. Now, because coil B is right next door, that changing magnetic field basically washes over it. And just like Faraday's law told us it would, that change causes a voltage to appear in coil B, all on its own. And just like that, we've sent energy across the gap.
And of course, in physics, there's always a beautiful little formula to describe this. The voltage we create in the second coil, that's EM, is equal to M times how fast the current is changing in the first coil. Now, that letter M, that's the hero of our story today. M stands for mutual inductance, and it's basically a number that tells you exactly how strong that invisible connection is between the two coils.
So how do we actually measure M? We use a unit called the Henry, and the definition is actually quite elegant. If you have a situation where the current in the first coil is changing by exactly 1 ampere every second, and that creates exactly 1 volt in the second coil, then congratulations, you have a mutual inductance of 1 Henry. It's a really neat way to put a number on this invisible influence.
Now, this connection isn't just a fixed thing. You can actually design it to be stronger or weaker. There are 3 main ways to tune it. First, the number of turns or loops in the coils. The more turns, the stronger the effect. Second is their area. A bigger coil can kind of catch more of that magnetic field. And last, and this one is pretty intuitive, is how close they are. The closer you bring the two coils together, the stronger their invisible link becomes. Makes sense, right? So let's bring this all the way back to our transformer. Inside that box, the two coils aren't just close, they're actually wound around the same piece of iron. That iron core acts like a super highway for the magnetic field, guiding almost all of it from the first coil perfectly through the second one. This makes the connection incredibly strong and efficient, and that's what we mean when we say the coils are mutually coupled. And that right there is the transformer's secret. So, we've cracked the case of the transformer, but this amazing principle is literally everywhere. That wireless charger for your phone, that's mutual inductance. The electric motor in a fan, that's using it too. Even incredibly complex things like MRI machines rely on this. So the next time you drop your phone on a charging pad, you'll know exactly what's going on. Which leads to a fun question. What other devices can you think of that are using this invisible force? I really hope this look into mutual inductance was interesting. If you enjoy this little breakdown and learn something new, please do me a favor and hit that like button, share it with someone else who's curious, and of course, subscribe to Kognito Key for more explainers like this one. Thanks for watching.